So far in this course, we have encountered functions that are expressed in the form y equals something, such as y equals 3x squared minus 2x, or maybe we've had to solve for y from a given relation. So another example would be y cubed equals x, and that doesn't look like y on one side and some function of x on the other side, but if you take cube roots, this can be re-expressed as y equals x to the power 1/3. And in everything that we have done so far, once we have a function y expressed as a function of x, then we take the derivative. We might use that in order to identify max and min of the function y, or optimize the function y in one way or another. So just to start things off, the derivative of this first function is 6x minus 2, and the derivative of this second function here is 1/3 x to the negative 2/3. In this section, we're going to encounter equations such as the following: y cubed plus x squared y to the 5th minus x to the 4th equals negative 11. So this is an equation that if someone were to ask me to solve for y as a function of x, I would really not know how to do that. In fact, it's the typical case that if you have an equation, a polynomial equation with high degrees like degree 3 and degree 5, you often can't isolate y on one side of the equation and a function of x on the other. However, that does not mean that this equation is somehow untouchable. In fact, it still determines a function y of x. In fact, it determines more than a single function y of x. There's actually a bunch of different functions determined by this equation, but we will assume that we're dealing with exactly one of those functions, and we'll just call it y of x. So here's the question for section 2.8, implicit differentiation and related rates. Can we compute y prime of x even if we can't solve for y of x? The answer is going to be usually yes. And so I just should repeat before moving on that we are assuming that in this section that the equation that we're given actually does determine y as a function of x. And that is a somewhat existential statement, which is part of what makes mathematics, such as that we're studying, beautiful. Now, in order to see the ideas at play, I want to return to this example here at the top of the screen and try to compute the derivative, y prime of x, without solving for y. And the way I'm going to do that is I'm going to remember in my mind that y is a function of x, and I'm going to start with this equation at the top. I'll rewrite it below and compute the derivative with respect to x of both sides. So here's the equation y cubed equals x, and the first thing I want to state is that if y cubed equals x, then the derivative with respect to x of y cubed must also equal the derivative with respect to x of x. And I'll write that out now. So the derivative of y cubed is equal to the derivative of x. Now, if I'm going to differentiate the right-hand side, that's pretty easy. It's just 1. But to compute the derivative of the left-hand side, I have to remember that y is a function of x. And so really, I need to use the chain rule. And let me do that now. So the derivative of y cubed with respect to x is 3y to the power 2 times the derivative of the inside function, and the derivative of the inside function is the derivative of y, that's just a dy by dx. So the equation is 3y squared dy by dx equals 1. Now this equation looks a little weird, but I should be able to take this equation here and actually solve for dy dx. So here I've rewritten the equation, and now I just want to divide both sides by 3y squared. So over on this side it cancels, and I'm left with dy by dx equals 1 over 3y squared. Now if you're looking at this, you're probably saying, well, hang on a minute. Y prime is the same thing as dy by dx. So the formula that we just derived right here, y prime is equal to 1 over 3y squared, doesn't look like this formula up at the top of the screen. Y prime is equal to 1/3 x to the negative 2/3. And that's okay, because in this equation at the bottom here that we've just derived, the derivative y prime is expressed in terms of the function y. And so if I want to make this equation in the box at the bottom of the screen look like the equation at the top, I should try to replace y by whatever it is in terms of x. And the equation that I'm referring to in order to do that is this one. I'm circling it in red. Y is equal to x to the 1/3. I want to take that relationship, defining y in terms of x to the 1/3, and substitute this y in the equation in the box, substitute x to the 1/3 for y. So y prime is equal to 1 over 3x to the 1/3 squared. Now that is 1 over 3x to the 2/3, and that becomes 1/3 x to the negative 2/3, which is the same as the derivative that I found at the top of this screen. So this example, of course, we already knew how to compute the derivative y prime or dy dx by first solving for y, but the second method that I explained here at the bottom of the screen, that method is called the method of implicit differentiation, and it can be used in more complicated situations where you may not necessarily be able to solve for y as a function of x. So we'll return and do the exact same thing on this more complicated equation on the next screen. Okay, so here's that equation that I had written on the previous screen, and I'd like to use this as an example, and I have two problems to consider. First, find dy by dx by implicit differentiation. And second, find the slope of the tangent line to the curve at the point 2, 1. Now, if you're the curious sort, you might wonder, is it really the case that this point lives on the curve determined by this equation? We check that by plugging in x equals 2 and y equals 1 into this equation. So if I do that, well, I get 1 cubed, which is 1, plus 2 squared times 1 minus 2 to the 4th, and that simplifies to 1 plus 4 minus 16, and that is equal to negative 11, which is the right-hand side of this equation up here. Okay, let me delete that. So it's useful to remember that there is a curve that passes through the points 2, 1 and is defined by this equation. The first challenge for us is to find dy by dx by implicit differentiation, and what we do is compute the derivative with respect to x of both sides of this equation. So I've written out that the derivative with respect to x of the left-hand side is equal to the derivative with respect to x of the right-hand side. So the thing to remember is anywhere where I see the letter y, I have to remember that that is actually a function of x. And so I need to remember to apply the chain rule. So the very first term here is a y cubed, and if I differentiate that with respect to x, I get 3y squared times dy by dx. That's using the chain rule. Okay, the next term is x squared times y to the fifth right here. And if I differentiate that with respect to x, I have to apply the product rule. So it's 2x, the derivative of the first term, times the second term, plus the first term, x squared, times the derivative of the second term, which I'll write out, d by dx of y to the power 5. And now I've applied the product rule, and I still have to apply the chain rule to this term here. The next term, I've taken the derivative of the last term in this equation. That's just negative 4x cubed. And to make it an equation, I put the equal sign, and the right-hand side is just the derivative of negative 11, which is a constant, so we get 0. Okay, so I'm going to rewrite this in order to compute the chain rule on this term here. So I have 3y squared times dy by dx plus 2xy to the fifth plus x squared, and now if I'm taking the derivative of y to the fifth, it's 5y to the power 4 times dy dx, the derivative of the inside function, because I'm applying the chain rule, minus 4x cubed equals 0. Okay, so this is an equation which has a bunch of terms, and two of these terms include dy by dx. And now all I want to do is solve for dy by dx. That means move everything else to the other side, simplify what remains on the left-hand side, and then solve for dy dx. So let me start by grouping terms. So here I've written the first term, 3y squared dy dx, and what I wrote next is the other term that includes dy by dx. So it has an x squared, a 5y to the fourth, and a dy by dx, and I organize it 5 times x squared times y to the fourth times dy by dx. And now I've added 2xy to the fifth, which is this term here. And I've subtracted 4x cubed, which is this term here. And that's all of the terms on the left-hand side of this equation, and that equals 0. So next, I have a common dy by dx in the first two terms, and I can factor that dy by dx out, and that's what I've done here, 3y squared plus 5x squared y to the fourth, all times dy by dx. And then I added the 2xy to the fifth minus 4x cubed is exactly the same last two terms. So the next thing to do is to move these two terms over to the other side, and I'll do that over here. So I just rewrote the first two terms, 3y squared plus 5x squared y to the fourth, all times dy by dx equals, and then I move these two terms, 2xy to the fifth and negative 4x cubed, to the other side, and I get a 4x cubed minus 2xy to the fifth. And now the only thing left to do in order to solve for dy by dx is to divide by this term right here, which yields this expression for dy by dx. It's important to remember that the expression we get for the derivative, dy by dx, contains both x and y, and you have to always remember that, okay, y is really going to always be a function of x. And this is the answer to part A. We have found dy by dx using implicit differentiation. The only thing left to do in order to solve part B is to plug the values x equals 2 and y equals 1 into the right-hand side. And I'll do that last step over here. And after simplifying, the slope of the tangent line to the curve at the point 2, 1 is exactly 28 over 23. And that's the answer to part B of this example. And that concludes this short video.